Good people. Here's something to look at. Here I have two objects. One of them we've already talked about before. It's this one, a pendulum. The other one we have not yet talked about, a spring. Now here's a question for you, is what do these two objects have in common? Take a minute, pause the video, and think about it for a second. Well, there are a lot of things that you could say that they have in common, but the one that's really important to us today is that they both move in very similar ways. They both have a back and forth and 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 back and forth kind of motion. The pendulum swings back and forth, and the spring bobs up and down like this. Any kind of motion that goes back and forth like that is what we call simple harmonic motion. And both pendulums, springs, and waves exhibit that kind of motion. Today, we're talking about springs. Now in these videos, one thing that you should know is that these are very raw cuts. So what we're gonna do now, normally in class would be a nice smooth transition, but what I'm gonna do right now is I'm gonna grab my computer, I'm gonna swivel it around, and we're gonna have a whole like resituating moment. Here we go. Okay, and there we go. Today, we're talking springs. Now, before we can talk springs, it's really important that we start by talking about this special kind of motion that you see that's exhibited by springs, pendulums, and waves. And this motion is what we call simple harmonic. Oh no, I'm doing the thing again that I'm trying to learn not to do. Okay, simple harmonic motion. Or sometimes we call it, go away. Sometimes we call it SHM, simple harmonic motion. Simple harmonic motion is any type of motion that is characterized by a back and forth, back and forth, back and forth. It's any type of motion that is characterized by oscillations, by an up and down, up and down, up and down, back and forth, back and forth, back and forth, back and forth. Any of those kinds of motion is called simple harmonic motion. So, pendulums exhibit simple harmonic motion, and springs exhibit simple harmonic motion. If you didn't write down the definition of simple harmonic motion, I would do that now. Simple harmonic motion describes any motion that is a back and forth, back and forth, back and forth kind of motion, or any motion that is oscillating. Any motion that is oscillating, any motion that is back and forth and back and forth and back and forth and back and forth, that's simple harmonic motion. If you need to, pause the video, make sure that you write down the definition. Now, that's a little on simple harmonic motion. For things that exhibit simple harmonic motion, they all have a few things in common. For example, all things that exhibit simple harmonic motion have periods and frequencies. Because if it's going back and forth and back and forth and back and forth, you could time the amount of time that it takes to do one back and forth, one oscillation. It also has a frequency. It has a number of oscillations per second. Yesterday, we learned about the skill of linearization, which helps us derive an equation for something. Today, we are going to use that skill of linearization to derive the equation for the period of a spring. You already know, just a quick refresher, you already know the equation for the period of a pendulum. It looks something like this, 2 pi times the square root of L over G. And we used linearization to find it. We made a bunch of graphs, we tested the variables that we thought were important, and then we found out that the variable that makes the true equation is the square root of L. Well, now we're going to do something very similar, except we're going to do something with springs. If you look at a spring, I want you to start by making a guess. What factors could possibly influence how long a spring takes to bounce up and down? You'll notice on this spring I've placed several weights on the bottom. You'll notice I can take off these weights to change the amount of weight that's on the bottom. There are other things I can change too, like I can change how far down I pull this thing before I let it go. We call that the amplitude of a spring. So those are some of the things that I could change. We also know that G is a factor in the period of a pendulum. So that's something to consider. Does where I am on Earth determine the period of a spring, or if I'm on the moon or somewhere else? So those are all different factors to consider. Can you please, in your notes right now, make a list of what you think some possible factors are that might influence how long it takes for a spring to go up and down? Hopefully, you have a good list in your notes of possible variables that could impact the period of a spring. When I did this, I came up with a list of 3 things that I thought might possibly impact the period of a spring. So here are a list of possible variables in the period of a spring equation. Possible variables. I said one possible variable could be the amplitude. The amplitude of a spring just really refers to how far you pull it down before you let it go, or for some springs, how far you push it up before you let it go. That's the amplitude of a spring. There's a little more to it there than that, but we'll get to that later. Then another factor that I thought might be influential is the mass that I put on the end of a spring. The last factor that I thought might be influential was G, the acceleration due to gravity. And I thought maybe if it were different than the motion, the period of a spring would be different. Once you have the variables that you think are important, the next thing to do is to test these variables and then to graph each of these variables. We learned yesterday how 3 different graph shapes can tell us different things about those variables and about how they fit together in an equation. Well, here's what I did. I took some data of some springs, and I took data of all the variables that I think might matter. Here's the first one. In each of these cases, I had a spring and I pulled it down to different points. First, I pulled it down 3 centimeters and 5 centimeters and 7 centimeters, 9 centimeters, and 11 centimeters. And I got the following periods. Then I put that on a graph. Hey, take a look at that graph of the period of a spring versus how far I pull it down. Take a second and look at it. Interpret it in your head. What does this mean about the amplitude of a spring and the period of a spring? Hopefully, your brain just said, well, it looks like the period of a spring and the amplitude of a spring aren't at all related. That's true. A nice flat line means there's no relationship between the period of a spring and the amplitude of a spring. It doesn't matter how far I pull it down. Very similar to with pendulums, where we saw that the height doesn't matter. The reason why the height doesn't matter, I'm going to go over here. The reason why the height doesn't matter is because if you pull it up to a certain height and you let it goes faster when it falls, but also it has further to go. And so further to go and going faster cancel each other out, and the amount of time is the same. Similar situation with the spring. You pull it down further, it has further to go, but the further you stretch it, the more the spring says, ah, and then it will pull back even harder on this thing. It'll bounce up and down even faster. So it goes faster, but it also has to go further, so they cancel out, and the amount of time it takes to do it back and forth is the same. So there's that. We know that amplitude doesn't impact the period of a spring. Let's look at some other variables. The next variable that I looked at was the mass on the end of the spring versus the period. In other words, how much mass did I put down on the bottom here? I started with 0.02 kilograms, then worked my way up to 0.15 kilograms. When I did this, I graphed it and I found that my graph looked like this. And I want you to take a moment, pause, and interpret this graph in your head. What do you think this data says about the period of a spring and its mass? You should have said that there's definitely a relationship between the period of the spring and the mass on the end of the spring. Hey, look at that. It's a nice curve, straight line. Which one? Hard to say. Do your best to eyeball it. Does it look straight? Does it look curvy? Well, there's one way to know. We could try to plot the period versus other versions of the mass. Like, what if we plot the period versus the mass squared, or the period versus the square root of the mass, like we did with the length of the pendulum? Well, let's see what we could get. If I graph the period versus the mass squared, then you see I get a very, very definite curve here. That says to me that period and mass are definitely related, but it's definitely not period equals a constant times the mass squared. That's not the equation for a spring. In our quest for linearization, we'll keep going until we get a graph that's a nice straight line. Let's try graphing something else, like period versus square root of the mass. If we graph period versus the square root of the mass, whoa, go back, you can see, wow, very, very nice straight line here. And this does, in fact, end up being the true relationship between period and mass for a spring, is that the period for a spring is directly proportional to the square root of the mass. In other words, if we go back here, let's write down what we found. Okay, over here, let's change my color. We shall make it blue. This blue, yes. Okay, none of that, please. Bye. Okay, here's what we found. With the amplitude, there is no relationship because we had a nice flat graph, so we know that that's true. With the mass, we know that T is directly proportional to the square root of the mass. In other words, the final equation is going to equal T equals a constant times the square root of the mass. Let's take a look at G and how the acceleration due to gravity impacts the spring. When I did this experiment, after testing the mass on the end of the spring, I took my spring to various planets and I tested out my spring at various accelerations due to gravity. So here you can see, here's my 9.8, that's on Earth, but then I went to a few other planets here, and you can see when I went to those other planets, I got different accelerations due to gravity. We have like Mercury here and Saturn here, so I went to a few different ones and got a few different accelerations due to gravities, and then I tested out my period. And you'll see that when I graphed those two things, I got a graph that looks like this. Interpret in your head, what does this mean? Did you say that there's no relationship between the period of the spring and the acceleration due to gravity on other planets? Because if so, you would be absolutely correct. There is no relationship between the period of a spring and the acceleration due to gravity. Now, a lot of students say, "What, Miss Wilson, that makes no sense." It made sense to us yesterday that the period of a pendulum, would be related to the acceleration due to gravity. And the reason why that makes sense to us is because isn't gravity what makes a pendulum go? And some of you are looking at this situation and you say, well, isn't gravity making the spring go? No, gravity is not making the spring go. Here's how I know this is true. Take a spring and turn it on its side. Do this same experiment. Take some masses on the end, push the spring in, let it go, and won't it still bounce back and forth on its side? Springs can work sideways. It turns out that gravity is not the go-go juice behind a spring, because springs can work on their sides. The go-go juice behind a spring is the spring. That's it. The spring constantly is trying to get itself to be the same shape as it was before you stretched it out. So every time you pull it down, it says, excuse me, no, I don't like being stretched out, and it tries to squish itself back up. Every time you squish a spring, it says, excuse me, no, I don't like being squished, and it tries to stretch itself back out. The go-go juice behind a spring is a spring. So we see, if we come back over here, that there is no relationship between the acceleration due to gravity and the period of a spring. You learned yesterday that the way that we find an equation for something based on a graph is that we use y equals mx plus b, and then we use our linear graph to derive the expression. If we go back over here, we can find that our linear graph here has a y, has an m, has an x, has a b, just like any other linear graph. If we could trace this back perfectly, and if my data was very, very nice and linear, you would see that actually b, my y-intercept, is right here at 0, 0. So when I set this equation, I'm going to say that my y-intercept is 0. Then, if I go back to my graph, my x variable in this case is the square root of the mass. So I'm going to go back over here and I'm going to call this the square root of the mass for my x variable. The slope is actually very hard to find in this instance, so I'm just going to call it slope for right now. We'll come back to that in a second. And then finally, my y variable, if you look at my graph, my y variable is the period of the spring. So I get an equation that looks like this. The period of the spring equals the slope of the graph times the square root of the mass on the end of the spring. Now here's where I'm going to give you some cheater points. If you looked at the slope of this graph, you would find that the slope of this graph is always equal to a constant. And that constant is 2 pi divided by the square root of k. K? Excuse me, Miss Wilson, what are you talking about? Great question. Let me tell you. K is a constant that is known as the spring constant. It's different for every spring, and it represents how easy or hard it is to stretch the spring. If it's really easy to stretch the spring, we have a really low spring constant. If it's really hard to stretch the spring, we have a really high spring constant, because K describes the amount of force you need to stretch a spring by 1 meter. K, the spring constant, describes the amount of force you need to stretch a specific spring by a distance of 1 meter. It's the amount of force. By the way, this is a definition that should be being written down right now in case you didn't get those vibes. It's the amount of force that you need to stretch a spring, a specific spring, by a distance of 1 meter. The units of the spring constant are newtons per meters, because it's how much force you need to stretch a spring by 1 meter. Pretty sensible units there, yeah? This means that overall, our equation for the period of a spring depends on 2 things. First, it depends on the mass on the end of the spring, which should make some sense to us, because more mass has more inertia. And if it has more inertia, it's going to be harder to get it to go. If you have more mass, your period will be longer because it's going to take longer to accelerate that mass. The second thing that it depends on is the stiffness of the spring, or K, the spring constant of the spring. If the spring has a really big spring constant, it's going to not be super, it's not going to be super stretchy. And the stiffer the spring, the shorter the period, because it's going to be really, really quick to just snap back into its old place. So this gives us a final equation for the period of a spring that looks like this. The period of a spring is equal to 2 pi times the square root of m over k. Put that in a nice box, and yes, that equation is worthy of your second semester Psychic Bag of Tricks. This equation, notice how similar it is to the equation for the period of a pendulum. Doesn't that make some amount of sense to you? They're really like kind of the same thing deep down. It's how long it takes to do it back and forth. Wouldn't you expect to see somewhat similar equations? So that should feel good to you. There's a little bit on the period of a spring, but that's not everything that there is to know about springs. There's actually 2 more things that we really need to talk about with springs today. The first thing that we need to talk about with springs today is we need to talk about a concept called Hooke's Law. Let's grab ourselves a new page here. We got to talk today about, let's change up our color here, purple. We need to talk today about Hooke's Law. Hooke's Law. Now, when we talk about Hooke's Law describes how springs actually work. Hooke's Law describes how springs actually work. Let's take a look at our spring again here. Hooke's Law describes how springs actually work. Now, here's how a spring actually works, if we're like really looking at it deep down. You pull down on a spring, and the spring pulls back up on you. That's what we call the spring force. That's what we call the spring force. If you push up on a squishy kind of spring, like the ones that live inside of your pencils, if you squish a squishy spring, that spring will push back down on you with another force that we also call the spring force. The spring force is this force that's always trying to oppose whatever you're doing. If you're stretching out the spring, it's that spring trying to say, no, go back to the middle. If you're squishing a spring, it's that force trying to say, no, go back to the middle. The spring force always points back towards the middle. And the operation of the spring force is how springs work. If you squish a spring, that spring says, no, go back down towards the center. Then when it stretches out again, the spring's force says, no, go back towards the center. Then when the spring squishes, the spring force says, no, go back to the center. And so then, because the spring force is going in the opposite direction of the motion, always, you have a little oscillation action where this thing is always going up and down and up and down and up and down. Hooke's Law is an equation that tells you how big the spring force is. Hooke's Law is an equation that tells you how big the spring force is. In other words, how hard is the spring trying to pull back to its original position, or to what we call its equilibrium position at the middle, at its nice resting point. So Hooke's Law describes the spring force and describes how you can calculate how big that spring force is. Well, we could use a linearization tool to derive this equation. But for the sake of time today, I'm just going to tell you what it is. Here's Hooke's Law. Wait, we'll go back here. Okay, here's Hooke's Law. Hooke's Law says that the force, I always do this thing, guys. Don't worry, I will get better. I have a nice growth mindset. I believe in my ability to improve. Okay, great. Hooke's Law says that the size of the spring force is equal to negative k delta x. It is a force, so it does need a vector hat, and this is a displacement, so it does need a vector hat. Add that to your bag of tricks. The spring force is equal to negative k delta x. See if this makes sense to you. Let's talk about k. First, you remember that k is my spring constant, and it tells me the stiffness of a spring. If we have a big K, it's more stiff. If we have a lower K, it's more stretchy. If you have a really high K, that means that the spring is very stiff. It's very, very hard to stretch. In other words, it really, really, really likes being in its equilibrium position. It takes a lot to get it out of its equilibrium position. If you have a spring that has a really, really big spring constant, it should make some sense to you in your brain that the spring force is also going to be really, really big, because the spring force is how hard that spring is pulling to get back to equilibrium. If the spring really, really doesn't like to be stretched or squished, then it's going to pull really, really hard to stay in equilibrium. That's the first factor. The second factor is delta x, which is the displacement. This should also make some sense to you. When we talk about displacement, we're talking about how far from equilibrium, or from the spring's resting position. Here's something that should make some degree of sense to you. When you pull down this thing really, really far, like way far away from the equilibrium position, the spring is pulling back even harder to try to get back to that equilibrium position. If you pull it down just a little bit, the spring force is like, we're pretty close to equilibrium position, and it doesn't pull back as hard. You know this because as you pull down, it gets harder and harder and harder to keep pulling. Why? Because the spring force, which is trying to pull back against you, is getting stronger and stronger and stronger. The harder you pull on a spring, the harder that spring pulls back on you. The further you pull a spring, the harder the spring pulls back on you. Likewise, if you had a squishy type of spring, the further you squish a spring, the harder, you can imagine one of those ones in your pens. The further you squish a spring, the harder and the harder and the harder it gets to squish. That's because the spring force pushing back on you is getting bigger and bigger and bigger. So, it should make some amount of sense to you that the delta x is in this equation, because the further you pull it, the harder the spring pulls back on you. One quick note for vertical springs in particular, or springs like this one that I have right here. Hey, do you notice that right now, when this little spring is just sitting here, the weight of the masses is pulling it down, but the spring is holding it back up? And so because of that, the spring force is pulling up, the weight is pulling back down, and the two cancel out so that this thing stays exactly where it is. That means, quick tip for your homework tonight, that if you had a situation like this one, where you had a vertical spring that's at rest, the weight of the masses on the end of the spring will be equal to the spring force that's pulling them and holding them back up. That's a note for your homework. Let's talk about this negative sign right here, because it's very, very interesting. This negative sign is a directional thing. It's showing the direction of the spring force. Notice, this is a vector, and this here is also a vector. So we have to take care of our direction, and the way that we take care of the direction is a negative sign. This negative sign here means something very important about the spring force, and the thing that it means about the spring force, no, don't do that, please. The thing that it means about the spring force is that the spring force is what we call a restorative force. Because the spring force is always trying to pull back towards equilibrium. Here's why that negative sign is there. Take a look over here again. Do you see how if I pull down this way, the direction, okay. Do you see how if I pull down this way, the direction of my displacement is this way? But which way is the spring force going? The spring force is trying to get this thing to go back to equilibrium. So the spring force is pulling up. Likewise, if I were to squish this thing, I displace it up, but the spring is trying to push it back towards equilibrium, so the spring force is pushing down. Notice, if I pull down, spring force goes up. If I push up, spring force goes down. Do you see how the displacement and the spring force are always in opposite directions? We have a negative sign to account for this. Check it out. If your displacement here is a positive displacement, that means that your spring force has to be negative because it has to go in the opposite direction of the positive direction, the negative direction. If your displacement is in the negative direction, then your spring force will end up being in the positive direction. We call it a restorative force because it's always trying to restore or to undo what the displacement has done, to go back in the opposite direction. That's the significance of the negative sign, and that is Hooke's law. Can you take a second and explain to yourself why there's a negative sign here, why there's a K in this equation, and why there's a delta X in this equation? Take a minute, explain those 3 things to yourself, pause the video, and then come back when you feel really confident that you understand those things. There is one last topic that we need to cover today when it comes to springs. And that last topic for today is going to be spring potential energy. Whew, potential energy? Was that like Unit 4 of last year, Miss Wilson, of first semester? Why, yes, it was Unit 4. And yes, there are some things from last semester that you're going to need to remember. One of those things is potential energy. When we talk about a spring, you know that before we've talked about spring potential energy and also gravitational potential energy. Last semester, we mostly focused on gravitational potential energy. Today, we're going to talk about spring potential energy. Here's how spring potential energy works. I pull down on a spring. Whoa, it's super stretched. When I let it go, it bounces up and down. All of a sudden, that potential energy has become kinetic energy. That potential energy becomes moving energy. When I stretch it all the way down like this, it has a lot of potential energy and none kinetic energy. Then when I let it go, it starts to speed up, speed up, speed up, speed up, speed up as it loses potential energy and gains kinetic energy. Very similar to a pendulum sort of situation, yes? Then, as it keeps going up, now it's regaining potential energy as it's squishing the spring, but it's slowing down, slowing down, slowing down, slowing down until, for just but a moment, it stops. Then it turns around again with all potential energy, and then that potential energy becomes kinetic energy as it speeds up, speeds up, speeds up, speeds up. The spring has the most kinetic energy right when it's zooming through its equilibrium point. It has the most potential energy on the ends when it's all the way stretched out or all the way squished up. That's how potential energy and kinetic energy work for a spring. But let's see if we have an equation for them. I'll give you a hint, we do. Let's talk about spring potential energy. Here's a little on spring potential energy, a quick equation. You know that when it comes to potential energy, we represent potential energy with the letter U, because you have potential. I'm sorry, I will never do it again until the next time I talk about potential energy, and then I will definitely do it again. The equation for spring potential energy is equal to 1/2 K delta X squared. 1/2 K delta X squared. Notice that potential energy of a spring depends on 2 things, and this should make a little bit of sense to you. One thing it depends on is K, which is the spring constant for a spring. If it's a stiffer spring, you're going to have more potential energy there because it's trying even harder to get back to equilibrium. And then also it depends on your stretchiness here, or how far you've stretched out. If you've stretched it out further, you'll have more potential energy because you've loaded this thing up. Doesn't it have more potential to go faster now? Notice, check it out, which one is more important, K or delta X? If you take a look, you'll see delta X is more important. Why is it more important? Because of this squared factor here. If you double the distance, you quadruple the potential energy. But if you double the spring constant, double the stiffness, you only double the potential energy. This equation is absolutely, as with most of our equations here, worthy of your Psychic Bag of Tricks for this semester. So you should have added 3 equations to your bag of tricks today. 1 for the period of a spring, 1 for the spring force, and lastly, 1 for spring potential energy. Oh man, And I ended with a little there. Good times. And that's all for today, folks. If you want to check out the calendar, you can find your homework there, or perhaps I can find it right here really quickly if I flip. Oh my gosh, I was so unprepared. Okay, yes, here it is. Your homework for tonight is page 371, numbers 1 through 4. Also, page 172, numbers 1 through 2. Oh, darn, I do this every time. Numbers 1 through 2. Also, page 381, numbers 1 through 2. And then finally, please read and take notes on 11.3. And that is all for today, folks. I did not do a practice problem together in this video. I will make a separate video that has a practice problem with springs, so that if you want to take a look at that, you are more than welcome to check out that practice problem. Have a wonderful rest of your day, and I'll see you all later.